Okay, welcome. Today we will cover classification. We'll talk about two classification methods, but first we will do like a brief discussion about the project. Can everybody hear me all right?
Yep.
Okay, so a lot of nodding heads, great. So yeah, it's time to start thinking about your project. And I kind of like just wanted to give you a brief introduction about everything related to the project. You can find all of this information also on the website. And the slides are also part of the repository for the lecture today. So what you kind of need in the very near future is you need to establish a team of 2 to 3 people. And then you also need an idea, like what is the thing that you want to do? You need to find a data set. And like an important caveat here is that you actually need a data set, not just like one, not a theoretical data set, but one that you can actually get. I'll talk a little bit more about that. And if you're unsure about like where you could get data, you could go to the website and look at the resources webpage. Generally, like we encourage you to also kind of collect your own data, for example, by scraping or by working with an API. But I'll talk a little bit more about this also later. The project kind of like has several phases. Things that you should kind of like start about thinking about quickly is like what's roughly your idea, what's your team, what's your project title, because on March 17th, we need you to announce your title and your team via a Google form. The link to that Google form is in the on the website, but I'll also post it later today on just in the announcement channel. And that kind of form helps us to, like you filling this form out helps us to set up the groups on Canvas where you then can submit stuff and also kind of assign like a staff member to be your mentor for your project. By March 26th, we need you to submit your project proposal. I'll talk more about what's in the project proposal later. Then we'll have an in-class session where we will get and give peer feedback on March 30th. So the way this will work is that you all come to class and then I'll set up breakout rooms. Like we set up breakout rooms for the groups. And then you pitch your project idea to another group, and the other group gives you feedback. And then after 45 minutes, we exchange the roles, and then you are receiving feedback, or you are giving feedback on the other group's team. And historically, this has been like very successful, and people really like that. You also get written feedback from staff, from your mentor, by April 4th. So this is like within a week after you submit the project. And then like the first really big milestone is the project milestone. And so you're submitting your project twice, once kind of like in an intermediate state, and a second time in the final version. But the milestone is kind of like it's pretty important in a sense. It also has a lot of points. It's actually worth much more than the single homework. But we also want you to kind of like experiment a little bit and get a feedback and give you an opportunity to catch any mistakes that you're running for like the later final submission. After the milestone, you will have a meeting with your whole project team and your mentor using individual appointments in the week of April 12th. So this will be like a 30-minute meeting where your staff or your mentor will have looked through your project, but then you also pitch your project, you explain what you've done and like what your next steps are, and then you kind of like get to kind of talk to your mentor about like whether you're on the right track or whether you should make any changes or anything like that. And then we have a final project deadline on Sunday, April 25th. And then finally, we will discuss the best project, show the best videos for these projects in class on April 27th. So like what do we kind of like expect from your project? So the scope is roughly like you should get an idea of the scope, but if you're unsure, just ask us. Come to our office hours, especially Anna's or mine, to talk about your project, and kind of we can give you an idea of whether you're on the right track. But typically, we would expect that each project contains like a data acquisition step, such as like web scraping or downloading data from an API. We also recommend that you consider multiple data sets. So for example, if you want to do a COVID project, you might like download COVID data for states, but you might also download other data for states, such as, let's say, like poverty rates or kind of like economic indicators, or kind of like ethnic makeup of states and so on, and try to correlate those things. So if you have multiple data sets, it often gets much more interesting. Usually you will also have to do some data cleanup. Then we expect you to do some exploratory data analysis using visualization. And then very important is we expect everybody to do 2 different analysis methods on their data. And analysis methods here means like things like classification, regression, clustering, dimensionality reductions, or some NLP. Or any other methods. Like we'll cover network analysis pretty late, but you could also conceivably do network analysis. And you should kind of like evaluate alternative approaches for each one. So you shouldn't just like run one classifier on your data set and say that's it, but you should kind of like do the whole thing with cross-validation and with finding good parameters, and then comparing multiple methods, and then identifying the methods that are most suitable. Similarly, for clustering, you would run like different clustering algorithms, different parameterizations, and so on. And then one important point is also we want you to talk about ethical considerations of your data set. Like I'll talk a little bit more about that later. And so like the typical project should hit all of those data or these bullet points, but it's okay if you want to skip one of these, except for the ethics one, but you have to make it up in other areas. So for example, if you have like a pre-formatted, clean data set that you can download somewhere, we would expect some much more sophisticated analysis methods than if you do some very complex data acquisition steps. So like, yeah, essentially you can skip one, but you have to make up for it in some other area. And we would ask you also to be ambitious. You like come up with like goals, and maybe they're hard, and maybe we can talk to you about how hard these goals are. Don't be overly ambitious, but definitely be ambitious in terms of what you're trying to achieve with your project. And then you can kind of like in your proposal, you can also define your goals and categorize them as like must-have features or must-have analysis steps, nice to have, or there's this maybe thing, I want to use this fancy method, or I want to use like a large neural network on a very big data set that could be like an optional feature if you get to it. So to talk a little bit about the ethical considerations, what we want you to think about is, were in the process of your analysis, were any ethical decisions made, and what were they? And it's very rare that you can actually say there is no ethical concerns at all about a data set. So that's typically not like saying like there's no ethical concerns about this data set is not like a section as you would expect, as we would expect it. So one thing you could try to do is a stakeholder analysis. Like, who are different personas that are relevant to your project? Maybe there's the analyst, maybe there's like the people that are in the data set. If it's about individuals in any way, maybe it's the people that consume your data. Maybe it's some people that are indirectly affected. How are they influenced? How does your analysis process influence these people? What are some incentives that may align or compete among these groups? And then it shouldn't just be about your analysis, right? You should also think about like the data itself that you acquired. Is the data that you collected biased or unbiased? So for example, if you were to look at vaccination data for COVID, the data of like people are not being vaccinated in a completely unbiased way, right? We know that like wealthy and white people tend to like get vaccinated at a much higher rates than other people. So like your analysis didn't do anything biased here, but you definitely should still discuss these biases in the data set. And then of course the central question that you should ask is, are there certain groups that would be disproportionately affected by analysis or by the data? So think about kind of like housing data, or like making decisions on credit scores and so on. All of this will like probably not equally affect everybody. Generally for the project, there's a couple of things that we've seen go bad over the years. And so here's a couple of explicit recommendations of things that you should not do. So do not use a standard machine learning data set. There's lots of these out there. There's like Kaggle or there's the UCI machine learning repository. This is not a machine learning class, right? Like we're not teaching you to write new methods. You're just applying more or less standard methods out of these libraries. And so just using one of these standard machine learning data sets is actually fairly boring. So that should not be your project, right? So it's OK if you like want to use one of those existing data sets, but have like 2 other data sets that you scraped yourself, right? If you want to mash them up in some way, then it's fine. But your project definitely should not be, oh, I downloaded a Datanic data set from Kaggle, and now we'll do some classification on it, right? That's what we're doing in lecture to demonstrate these methods, but that's not a data science project. And don't pick a data set where structured data is really hard to extract. So for example, don't pick just text files and expect to get something out of it with advanced NLP, like advanced sentiment analysis or something like that, unless you really know what you're doing. If you've taken an NLP class before, that might be OK. Don't try to extract data from collections of PDFs or from something like handwritten data or anything like that. I've once had a project that wanted to analyze Supreme Court cases from court decisions that were available in PDF. And I told them this is going to be really tricky and dangerous. And then after the milestone, they had to pivot because they couldn't get the data out and had to start over with a completely new project. So this was kind of like a really unpleasant situation for this team. And the other thing that you should probably not do is running your own survey. It can be tempting, right? If you're like doing something related to students, you could conceivably run a survey among students, but this is really hard to do. And it takes a lot of time, and we're not talking all that much about it. So I recommend that you don't run your own survey. Any questions so far? OK, so then I'll talk a little bit about the proposal and its sections. So in the proposal, you should have some basic info like your names, your contact information. Why did you pick this project is the next part, and what's your motivation? What are the objectives? What are like the bigger picture analysis question that you're trying to answer in your project? What is the data? Where will you get it from? By which process will you acquire it? What are the ethical considerations that you can foresee? What are the expected data processing steps? What are kind of like roughly the EDA steps that you're planning to do? What are the kind of analysis methods that you want to apply? Here we can like you should think about, is it a classification problem? Is it an unsupervised learning problem? And so on. And what's your schedule, right? Like more or less like which of these features or which of these aspects do you want to have done by the milestone, and which of these aspects do you want to have done by the final project? And then once you have written this proposal, like we expect this is something like 3 to 4 pages maybe. You submit this either as a PDF or as a Jupyter Notebook to Canvas, one submission per group. So we'll set up these groups for Canvas, and so like you submit this only once per group, and then everybody is graded together in the group. For your milestone here, we expect you to have like the acquired and clean data. We expect you to have done exploratory data analysis, and you should have kind of like sketched out your analysis method. So you should have tried maybe run a classifier, but maybe you haven't done cross-validation or haven't compared it with like between different methods or something like this. And then for the milestone, you submit a zip file with your Jupyter Notebook, the data, or other resources. Again, only one submission per group. And then, oh, by the way, you can, of course, use multiple notebooks. So you could, for example, have like a scraping notebook, and then you could have an analysis notebook. But there should be like one main notebook where you have links to everything else so that we know how to read this. And then your final submission is the whole story in a notebook with potential links to other notebooks. We also do want you to interpret your data. Like interpretation isn't something you need to really do for the milestone, but in your final project, we want you to analyze the data and you to reason about what you're seeing and to make explanation and do inferences. And we also want you to create a 3-minute video that narrates your project. That 3-minute video can, like typically, you can do a screencast, right? And just walk us through your Jupyter Notebook. Or you can do like a PowerPoint or Keynote presentation with the key figures and results in your notebook. and narrate it this way. So how you do this exactly is up to you. It's supposed to be 3 minutes only. The reason why we asked for this video is because this is a fairly big class, and ideally we would love to do project presentations from every group, but that's just not realistic with like 100 students. And so we'll take these videos, and then we'll be watching the videos, and we'll be also using these videos in kind of like our first pass for decision making for determining the best projects. So the projects are group projects, and there's a couple of reasons why they're group projects. First, it's kind of like logistically easier for us, of course, to handle 30 groups than 100 with 30 projects than for us to handle like a full 100 projects. But we also think there's value in group work. So make sure to be fair to your team members. Like if you agree to do a certain part by a certain time, then do it. Don't be behind. Don't like delay the project. So just make sure that you stay within the schedule you agreed upon. And if you're like running into issues, just be very upfront about it and tell your team members that you're struggling with this, you need help, or you don't have time, or you're sick or something like that. Just be upfront about it, and then usually there's a good solution. Do communicate with your teammates immediately if there's a problem. But if this problem is kind of like unsolvable within the team, do reach out to us if that problem is serious, and do that early. Like often it helps if I kind of like meet, or Anna or I meet with a student that is like not doing their share. They will afterwards sometimes like find the time or like refocus to actually get something done. It's really, really hard for us if you tell us like the day before the project is due, my team member has not done anything that he or she was supposed to do. So that's really tricky for us. The sooner you tell us, the easier for us it is to step in and help and fix something. If you want to have a bit of an like, what is the scope? There is a Hall of Fame where we show best projects from 2018 and before. So these are useful. And yeah, this gives you kind of like an idea of the scope. So with that, any questions about the project?
Can we run project ideas by you at some point if we want to just kind of get like, like, what do you think about this one?
Yeah, you can do that either on in our office hours, or you can also write us an email.
Okay, thank you.
So with the project, is it expected we're just going to do it all through Jupyter Notebooks?
Yeah, so you should do it in Python. You can do it in Jupyter Notebooks or in Google Colab, right? Which is just like a Google Docs version, more or less, of Jupyter Notebooks. Colab has the advantage that you can collaborate more easily. It has a couple of disadvantages of like data loading is a little bit more tricky. But Colab is something that I would recommend for group work, and you can download a Jupyter Notebook from Colab.
Okay, and I mean, this is not in the scope of it, but I was thinking of setting up the project ultimately maybe on like a live site, so it's like accessible. Would that be like, I mean, that's out of the scope of the class, I know, but would that be like okay to?
What you do with your project afterwards, whether you add this to a portfolio on your website or whether you host it on the Jupyter Hub somewhere, that's totally fine with us. It's kind of like you own your project. Other questions? Well, if not, let's move on to classification. Okay, so this is our first kind of like classification lecture. Classification is also often called like is a part of supervised learning. And in this lecture, we'll discuss kind of like generally like what is classification, how does it work? This is actually wrong. It's not logistic regression. We will cover k-nearest neighbors and decision trees. Okay. And then we'll talk about model generalizability and cross-validation. Okay, so what is classification? In like compared to regression, in regression, we try to predict some real value for an unknown variable. So for example, we want to predict house prices based on attributes. This is like roughly what you could have done in on a real estate data set. Or predict credit score rating based on income, balance, gender, like your account balance, gender, education, and so on. And so here, like we try to predict a real value. In classification, we typically try to predict a categorical qualitative variable. So for example, whether a bank should issue a person a credit card, yes or no, or predict whether a hospital patient's diagnosis, what a hospital patient's diagnosis is. For example, based on their symptoms. So based on the symptoms, do we think that this person has a stroke, a heart attack, or something else? And the way we do this is we assume a data set with n samples and xi attributes or features. And then for these samples or features, we also have categorical variables that we want to predict, the y's. And like in classification, our goal is to develop a rule for predicting these categorical variables y based on the features x. So for example, can we predict whether or not a student will be admitted to a graduate program based on their undergraduate performance, like GPA, GRE score, prestige of students undergraduate or university, and so on? These could all be features that we use. And then we want to use like prediction to see whether we can actually do that. And like one thing that you immediately see here is some of these problems are never going to be completely solvable, right? So some of the predictions are like that we'll be trying to make will just like there's just not going to be like a way to get every single decision correct with machine learning. Another example where we'll actually be trying ourselves is if we want to classify handwritten digits. So let's suppose like the post office uses machine learning to read like handwritten zip codes to classify it, to pre-sort the mail. This is something that they actually do, right? And so what you can do is you can take a digital picture of the zip code, you can separate it out into separate numbers, and then you can take those little pictures with these numbers and treat them as a feature vector. And you want to predict a certain class from that picture, and these classes are the digits, like 0 to 9. And so this is like the MNIST data set, for example, is something that is commonly used for exactly this problem, and it just demonstrates that like an image is just like an array of grayscale values, right? And with machine learning methods, you can actually treat this just like as a vector of other observations. So
Dr. Lex, you mentioned that problems might not be solvable. Is that because the classifiers are not separable?
Yeah, exactly. So for example, you will never, like, you might not have enough data, and there might be, like, for example, if there's human decision-making involved, like admitting a student to a school, like there's a faculty or like a committee that reviews a student's application, right? What exactly that committee thinks is just like not capturable at all. And you have other data, like, for example, the need of the faculty in a particular area and so on, that you just never can capture. So there will be kind of like data sets where you can get like a pretty high accuracy, but never a perfect accuracy. Okay, so we will cover several of these like classification methods. Today we'll cover k-nearest neighbors, decision trees and random forests, and then in the future we'll cover logistic regressions, support vector machines, and then neural networks and deep learning eventually. And some of these methods can be used mostly for classification, but many of them can also be used for regression. So we'll talk a little bit about regression, but mostly today we'll be focusing on classification. Okay, so let's talk about our first method, the k-nearest neighbor method. And here the idea is actually very simple. To decide the class of a given point, which I don't know, find the k-nearest points of that point and let them vote on the class. So we assign the class to the sample that is most common among its k-nearest neighbors. And I want to show this, like, catch this quickly. Let's see. Okay. Everybody should be able to see my iPad now. Is that working? Okay.
Yep.
Okay, let's suppose we have a data set here where like we have like two-dimensional data set in X and Y, and we have two classes of points, the red points and the blue points, right? And so if we had assumed like a K of 1 and we were to assign, like we were to create a new point, or try to find the class of a new point, and I draw this point over here, well, it's not particularly hard to understand what that point would be. We would look at what is the closest point here. We would say, well, it looks like this point here is the closest, so we have the minimum distance. Hence, we assign red to this point. Similarly, if we had a point over here, we could run like we could measure the distances, find the closest point for a K number 1, and then assign a class based on the class of this point here. Okay, so that's fairly easy. If I have a point somewhere in the middle, it's kind of like not obvious, but there will be like one point that is just a little bit closer than the other point. So in this case, it probably would still be the red point here. So this would be a red class. So that's kind of like the idea of a K nearest neighbor with a K of 1. But as you can imagine, this gets a little bit trickier if I have a data set like this here. So it still looks like I have a pretty good decision boundary here. So most points that are on this side of the decision boundary will be on the blue side, and the points that are on this side of the decision boundary will be the red points. But that's not perfect because our data isn't perfect, right? So as I just said, like sometimes we don't have enough data to make these items perfectly separable. And so let's suppose I have a point that I want to like classify that is around here. If I have a K of 1, I would just like probably use this point, and then I would assign it like a red label, and we could probably argue that this is correct. But what about if I have a point here? Then I would find this is the nearest point, and I would like, if I use just a K of 1, then I would think that this is actually a blue point, which is arguably like not the right classification, right? So this is strongly influenced by this one outlier that is outside of the place of the usual blue points. So now let's look at what happens if we have like a higher K. Let's say we have a K of 3. Now, if we were to ask for, let's say, this point, we would just take these 3 points here and let them vote. All of these 3 points are red, so there's really no ambiguity. We will just assign that point the red class. Let's suppose now we have a point that is here. We could now like do the same thing and look for the 3 closest points. And if we just let them vote, we will now correctly classify this point here as red. And so what you can see here is that by varying K, I will get kind of like models that are different, that are more specific, that have kind of like have different levels of complexity. And so if I had like a very high K, like I might end up with like a pretty simple decision boundary of maybe something like this. The other thing that I could use is I could use distances in here, like how far is this point away? How far is this point here away from this point? And kind of consider that in the voting, right? Especially if I have higher Ks, I could kind of like weigh the voting process by the distance to a certain point. But the most important thing in K nearest neighbors is to kind of like just figure out what is the right K. So, okay, does that conceptually make sense, or any questions?
I do have a question.
Yeah.
What if you have, if K is equal to 3, but if you have 4 points that are equally or equidistant away?
Yeah, then you need to find some tie breaking, right? So like you can come up with different tie breaking methods. Like one method would be simply like if they were completely equidistant, and if they were like if you had exactly the same number of points in the two classes, you would just do a random pick. Or if they're not completely equidistant, right, then you would you could do something about it. You can kind of like, typically this isn't a real issue, right? But you could of course just use an odd number for k. But yeah.
Thank you.
I have another question.
Sure.
So how does the voting mechanism work? For example, for a K of 3, would a 2/3 of the vote make a decision?
Yeah, exactly. Well, you can come up with your own voting mechanism, right? But 2/3 of the like a majority would be useful, right? Or you could have a weighted majority, and you can also kind of like well, one thing we won't be talking about, right? But you can also kind of give a confidence score. So if you, for example, have like 5 out of 10 or 6 out of 10 vote in one way and 4 out of 10 vote another way, you can still classify it as a red point, but you can also say that you're not completely uncertain. So if you do like image classification tasks, like if you use any of these fancy image classification websites, they will give you like, hey, this is a dog with like 0.9% probability, but it could also be a cat or something like that, right? So you could use something like that if you want to. But for binary classification, you essentially have to make up a rule, and different implementations might have slightly different rules. You can parameterize your algorithm, how you want to do that, but some kind of like majority or weighted majority voting is usually how you do it.
Okay, thank you.
Okay. So then I'll return to our notebook. So I want to start off with an example of a synthetic data set, which we call it 2 moons. Let me just see what I didn't run the imports. And the 2 moons, we have like the features here. And then, well, here, this is the make moons function. This is just like one of these like standard functions that we have in scikit-learn. I'll talk more about scikit-learn in a second. We will create those 2 moons. And so what you see here is essentially we have the red points that are in this moon shape here with some noise, and the blue points that have this moon shape here, blue squares with some noise. So we can say, well, these seem to be separable, but they're not perfectly separable, right? And so this is a synthetic data set. I'm kind of like specifying the noise here. So if I reduce the noise, then they will be more easily separable, but I don't want them to be completely separable. And so what I get here, and this is how this is going to work going forward, is that I have like 2 parts of the data set. I have my features and I have my labels. The features are always going to be X and the labels are always going to be Y. And so that's why it's also called supervised learning, right? Because we have these labels and we're trying to learn a model from these labels. And in this case, X here is a 500 by 2 NumPy array containing the coordinates for each sample, and Y is a 500 by 1 NumPy array containing the class for each sample. And down here, I'm just plotting this. And then I did plot, I manually picked a couple of points here, and I'm plotting those as crosses. And so we can look at these crosses. Like we would expect that the point here and this cross here is very clearly a red point, right? The point here is very clearly a blue point. In here, we would probably say this is blue. This here is pretty ambiguous. And here we have kind of like an interesting outlier condition where we have like 2 blue points surrounded by mostly red points. And so we'll look at how are these different points classified. And now for the big thing that we'll be using going forward, So far, we've mostly used a stats model, but going forward, we'll be mostly using scikit-learn. And scikit-learn is this like very famous Python machine learning library that has like lots of different algorithms implemented. And this is kind of like a very convenient way for us to like run all of these different things. And in particularly, we will use the k-neighbors classifier. And as usual, you have like good documentation that describes all kinds of different things. OK, so now the magic happens. I am running k-neighbors classifiers. Well, here I'm just initializing it. And this is like the important part. I'm setting the number of neighbors. I'm kind of like, I have 500 features. And so I'm setting k to be 100 as like a first guess. And this is how you train a model. You simply say model fit, and then you give it your data, and then you give it your labels. And then after we have fit our model, we can use model.predict for new cases. So now I'm using these 5 data points that I've set up here to try out how would they be classified. And so like you see, this was very fast. This happened more or less instantaneously. Now let's look at what is happening here. For my point 1, 5, minus 1, which is kind of like 1, 5, and minus 1. This is this point here. I have predicted, I have expected class 1, and I have correctly predicted 1. For my class minus 1, 1, I have expected 0, and I have predicted 0. For my for the point 0, 0.1, this is kind of like the borderline case on 1, and I have correctly predicted 1. 0 and 0.5 is borderline 0, and I have correctly predicted 0. And 0.5 and 0.75 is borderline 0, and I've predicted 0. So it looks like we've done a good job here. But now let's try what happens if we reduce our k. So let's suppose I set k to 1. Now I can see that there's something isn't quite right. So I have this borderline case that should be 0, but was predicted 1. So clearly, like picking a k matters. And so basically, the higher the k, the simpler our model becomes. And the lower the k, the more risk we run with overfitting, especially for unseen data. So I'll talk more about this whole idea, but I first want to show that you can also plot these decision boundaries. Like all of these examples that we're doing here are in 2D, so this is kind of like easy to plot. But if we just had a 2D plot, we could like for this classifier, we can show that like any point that would end up in the red area by our current model would be classified as a red point. Any point that ends up in the blue area would be classified in the blue point, in the blue part. And so the interesting part about this is, what do you think happens if I set my k to something very low?
The line will move up.
Can you say that again?
I was just thinking, at least that first line will try to grab more. Well, actually, I don't know. It might overemphasize this like kind of arch that's happening. That's my guess.
Yeah, let's try it out.
I'm thinking it won't deal with outliers as well, right?
Well, it depends on it. So like, it won't do with outliers so well. I guess it depends a little bit on, have you seen your data before? Like what you see now is that my decision boundary that was this like nice swooshy shape before suddenly is this extremely patchy thing, right? So like actually I have in this model now, I have kind of like classified every point correctly. The problem is that I've classified every point correctly only for the data that I've already seen, right? And for data that I haven't seen, I just like might be off. For example, like in particular, the example that I had up here, this point in here, that will just be influenced. Like you can see that this point here, I didn't plot it here, but this point is exactly here, right? So that point will be in this little blue island, and so therefore will most likely be misclassified. So generally, what we can say is that lower our k, the more complex our decision boundary. And maybe like if we try then eventually for new data, we will have kind of like like less accurate decisions compared to what we had on our training data, which is what we call like the model is overfitting to the training data. So that's the kind of like the thing that we always have to be mindful about.
Is there a limit on K? So if you can't make K equal to the number of points you have in your training set.
Yeah, so if you make K equals to your points you have, then you will just get a prediction for the most frequent point, or for the most frequent class, right? So in this case, there seems to be one higher, like one more red point than a blue point. And so you get everything is predicted as red. So like what you see is kind of like picking K really matters. Like if I do K of 200, I will probably get something smoother. And if I pick a K of, let's say, 300, I almost get a line. So now I almost have a straight line separating those two classes, right? Earlier I had like this nice swoosh that we know because it's synthetic data in Moon shape. That swoosh is exactly what we want. If we kind of like use a K that is too high, we get a model that is too simple. If we use a K that is too low, we get a model that is too complex. So picking K, and generally machine learning is all about picking parameters, so like finding the best parameters. And picking K, of course, is super important here. So what I've done so far is we've looked at some kind of examples that were handpicked to see how well our algorithm did, but there's more structured ways of evaluating a classification method. In regression, we had several methods for evaluating a model. We had the R-squared value, or we could run a hypothesis test associated with the model and individual predictor variables. But like, how could we do this with a classification method? And the most common or the most useful way maybe is the confusion matrix. A confusion matrix is a table where each column of the matrix represents the number of samples in the predicted class, and each row represents the number of samples in the actual class. So here is an example where we, for a classifier that is trying to classify 27 images of cats, dogs, and rabbits. And the confusion matrix for that for the classifier would look like this. So we have our actual classes and our predicted classes. And along the diagonal here, we have the correct classification. So we see that 5 cats were correctly classified, 3 dogs were correctly classified, and 11 rabbits were correctly classified. But then everything outside of the diagonal is like a wrong classification. But it's not only that it's wrong, we also know how it went wrong. So for example, here, this dog here, or 2 of these dogs here were predicted to be cats. Or one of the dogs was predicted to be a rabbit. Or 3 of the cats were predicted to be dogs. And there is no misclassification between cats and rabbits. And so what you can say is this model can actually separate well cats and rabbits, but it's pretty bad at recognizing dogs, for example. This is also like, we can use this, like another metric that we can use is precision and recall. These are like 2 key metrics that we can obtain from the confusion matrix for binary classification tasks. Precision here measures how accurately our predicted set contains only the desired classes. So for example, like, or specifically, a high false positive rate leads to low precision. And recall measures whether we accurately pick up all the cases in the desired class. So a high false negative rate leads to low recall. So here, precision is true positives divided to true positives plus false positives, and recall is true positives divided by true positive plus false negatives. And just like true positive and false negative, here's this humorous comic or humorous illustration. We have predicted values and actual values. True positive is if you correctly say that somebody is pregnant, for example. True negative if you correctly say that somebody is not pregnant. False positive if you tell somebody that they're pregnant if they're not, which is also called a type 1 error. And false negative is telling somebody they're not pregnant or like don't fall in this particular class when they in fact are. And we often like care about these rates very much. So for example, in COVID testing, especially in antigen testing, these fast tests, right? We just when we run such a test, we have better methods to eventually test. So it's okay for us in rapid testing for COVID to get false positives. So like antigen tests have like a 5% false positive rate. But then if you have a false positive, you can use a more precise method to make sure that like whether you actually have COVID. But a false negative would be very problematic for rapid testing, right? So you really want to make sure that you pick up every single positive case or as many as you can and really avoid false negatives. So precision and recall, you can also try to combine them into like a single metric, like the F measure, which is more or less the harmonic mean of precision and recall. There's also other measures like the ROC curve or the Jacquard similarity score that you can use to measure accuracy. And the nice thing is that scikit-learn provides these metrics for us. And so we can here like look at the confusion matrix. And this is for our MOONS data set, and we can see that we have 233 and 205 predicted correctly, and then we have 45 and 47 mistakes for the red and the green one. And then we have here our precision scores, our recall, our F score, and our Jacquard similarity score. Okay, before we move on, let's do our 5-minute break, and we'll resume at 1:17. Okay, so now let's try our KNN method on a real data set. And we'll use this super common iris data set for a demonstration. This data set was introduced in the 1930s by Ronald Fisher, a famous statistician. And this data set here contains 4 features of 50 samples containing 3 species of iris plants. And so iris plants are these lilies that look roughly like this. And what this data set is measuring is these 2 different leaves here, the petals and the sepals, how long they are and how wide they are. And this varies by species. And so the question we can answer here is, can we actually separate these species just by looking at sepal length, sepal width, petal length, and petal width, and ignore other attributes and characteristics such as maybe color and context and so on? The iris data set is such a common data set. We've already seen it. And when we looked at Seaborn, we'll load it from Seaborn, where it's one of the demo data sets. And we can first look at this in a scatterplot matrix. And in the scatterplot matrix, what we can pretty quickly see is that the Setosa species here tends to be very well separated, right? So it tends to have, across all of these different attributes, it tends to be essentially in its own cluster. So that's probably not going to be hard to tell the blue species here apart from the rest. But the orange and the green ones, there's some overlap. So these might be a little bit harder to tease apart. And so what we'll do first is we will look at this for just 2 dimensions. So in these 2 dimensions, we can see that, again, the blue species is fairly hard to tease apart, but the orange and the green ones are not so easy. So let's try to run a model with this. We set a k to 20, and then we run our k-neighbors classifier, and I'm also, again, visualizing the decision boundary. And so what we can see here is the decision boundaries are pretty complex with a k of 20. And it looks like we cannot completely separate our data. And so if we wanted to print the confusion matrix, we can see that there, as we expected, the first species, the blue species, perfectly separate. So we have all of them classified correctly and 0 errors, 0 misclassification errors, but we mix up the orange and the green one here, as we can see from the confusion matrix. So let's try to change k. Let's do something like a higher k. Let's see how that influences our results. Well, it doesn't make it much better. So we can keep trying that. And well, since we're doing this on the original data set, we can, of course, the lower we make k, the better it's going to be. But then it wouldn't really work for new data. So here, in this case, that we got a very high accuracy. So now we've only done this with 2 dimensions, but what happens if we do this on all of the dimensions that we have available? And that's really I can't really visualize this anymore. But if I just run this on the full iris data set here, you can actually see that I get a very high accuracy with a k of 20, right? So I get 98% accuracy, and we can see that there is very few misclassifications. So to recap, for larger k, the decision boundary becomes very smooth. The model is not very complex. It could basically be described by a few lines or by some simple curve. The model has low variance in the sense that the data, if the data were to change slightly, the model wouldn't change much because there's many votes. And because the model doesn't depend on individual data points very much, we expect that it would generalize to new data points. For a small case, we see that the decision boundary becomes very wiggly. The model becomes very complex, and it can't definitely be described by just a few lines. That model has high variance in the sense that if the data were to change slightly, the model would change quite a bit. Because if I move a single point around, if that one point corresponds to its own island, right, that would, of course, change. And the model is very dependent on the data set. So we would say it doesn't generalize much to new data points. We would say that this model has overfit the data. So how can we choose K? Anybody have any ideas of what we could do to actually choose K?
Is this where you do the cross-checking?
Yes, this is where we do the cross-checking. So I guess what I means is cross-validation. We can use kind of like methods to like try out different configurations with parameters. So what we want to do is we would like to develop a method on a data set where we like use a training data set that we will use to train the model, and then use separately a testing data set, because that allows us to, that was not used to train the model, because that allows us to understand how a model generalizes to new data. And so if a model that we trained on a training data set also works well on a testing data set, we say that this model is generalizable. So if a model has 100% accuracy on a training data set, for example, the K is one case, but doesn't generalize to new data, then it's not a very good model. And so we say this model has overfit the data. On the other hand, it would be difficult to see that we could also, it isn't difficult to see that we can also underfit the model, making K very large. And the model would be too simple to have good accuracy on the training data set. And so we can use this idea in kind of like this structured approach with cross-validation, where we assess a predictive model that works for classification and regression. And we talked about this for regression already a little bit, to generalize to an independent data set. In classification, cross-validation can be used to assess how well a classification model will predict the points that we use to train a data set. And so what we do is we split the data set into two groups, the training data set and the test data set, then train the model on the training data set, and then check the accuracy of the model on the test data set. In practice, it's not like a completely trivial question on how to split the data into groups. And you also might want to repeat your experiments for different splits of your data set, so you don't have some artifact. But we'll worry about this in a later lecture. For now, we'll just do like a simple split. So here I'm recreating the Moons data set, and then I'm using the train test split function that scikit-learn also provides. So I've imported this at the very top of the notebook. I pass in my features, I pass in my labels, and then I pass in some kind of like random state that that is used to initialize it. And then I'm saying how big do I want my test size to be versus how big is my training size. And so here I'm saying like I want 70% of my samples to be in the test size. And now I'm actually running cross-validation for multiple configurations of K. So I'm trying out Ks of 1, 2, 5, 10, 50, and 100. And I'm running this K-nearest neighbor for all of these different classifications for all of these different models. And so what we can see is for a K is 1, we have an accuracy in our training data set, and an accuracy of 1 at a perfect accuracy, and an accuracy in our test data set of 0.7, right? And so for K is 2, the accuracy in a training data set goes down, the accuracy in a test data set, well, it goes up slightly. For K is 5, we see that we're kind of like converging on something here. The accuracy of the training data set didn't go down much, but the test data set went up. And then if for larger Ks, for like a K of 50 or like a K of 10 even, these are very close. So we have like an 80% accuracy in our training data set and a 79% accuracy in our test data set. And so you can see that this is roughly where we end up. So this model actually performs worse on a training data set than on a test data set, but that's probably just, or that's certainly just like an artifact, right? So that's not something that you can usually expect. Okay, so I see there's a question. Might it be useful to scroll K interactively? I guess you're meaning trying out different Ks. So I'm assuming this question is supposed to be like, is it useful to scroll to try out different Ks? And yes, that's certainly useful. Typically, you don't try out every K, but you use some kind of like sampling strategy. Here, I've done something manual, but you could come up with some smart sampling strategies. Okay, so just to like really emphasize that point, here is kind of like an illustration of, we have this kind of like prediction error versus model complexity. And what we kind of like, if we have a model that is like very simple on our training data, then it will also like generalize, but not be super accurate, right? If we have a slightly more complex model, then it will have a low error on both the training data and on the test data. And so we're kind of like hitting the sweet spot here, that this is like the error is low on both the test data, which is the stippled line here, and on the training data. But at some point, if you start overfitting, your error will go down on the test, on the training data set, and you will have a very complex model, but it will not generalize well. So you will have like this, like for new data, for test data, you will not get good accuracy, and you're overfitting your model, which is clearly the case with what you're doing here. And so you really want to find this model that has this perfect trade-off between complexity and prediction accuracy. Okay, now we can look at these boundaries for the 2Moons data set. And so this is just like a lot of code, because I want to look at these different boundaries here, but it doesn't do anything that we haven't really seen before. It just like does it in kind of a more structured way. And this will take a second because I'm running this for like many different Ks. Okay, so now here we see kind of like how our model changes as we vary K. We have K from 200 to K1, and then we have our training and test. So basically, we are recreating the figure we saw here for our 2Moons data set. And what you can see is the accuracies are shown in here. And what you can see is that we have a very simple model, which has like an 80% accuracy in our training set and an 80% accuracy in our test set. But if we have a slightly more complex model, we get like 81% or 82% on these tasks. But as we reduce K and make our model more complex, we get higher scores for our training set, but lower scores for our test set. So like some conclusions here. KNN is a super simple method that can be used for classification. Now, how could you use it for regression? For predicting a real value? You could just, instead of like having classes and voting, right? You could just take, if you have a K of 3, you could just take the real value of your 3 neighbors, average it out, and then that would be your predicted value, right? So you could use KNN just as well for regression. Model accuracy and generalizability are both important and often in contention with each other, and we can measure model accuracy using a confusion matrix, precision and recall, an F measure, or the Jaccard similarity scores, and we can kind of like evaluate generalizability via cross-validation, and we can use cross-validation also to pick parameters in models. So we can pick those parameters, and as long as we have like computationally easy models like we had here, we can do that fairly efficiently. Okay, any questions about KNN before I move on to decision trees?
Well, from the image above, which model would we end up choosing again? The 8081?
Which model you would from these here? So you basically evaluate using cross-validation. You can validate or you can evaluate which model works well for a test set, and that's kind of like the model that you want to do. So here for this data set, it like seems to work pretty well for K is 50 and clearly not for a K is 1. Like whether you use 50 or K is 23 or 99 doesn't seem to make all that much difference for this particular model. But essentially, in this model, you just want to make sure that your K is like not too large and not too small.
Alex, can I just make a comment real quick here?
Sure.
Oh, so I just wanted to say one thing regarding the KNN classifier. So if if the size of your test data set and your training data set are the same, then that's great. You don't have to worry about it. One thing to keep in mind might be, the effect of the sample size. If your test data set is like twice as big as your training data set, then the sample size also, it directly affects the K that you want. So, so you might want to equate, like a K of 10 on the smaller data set with like a K of 20 on the larger data set,
Yes.
or just split them equally. But
yeah, that's a very good point. So your K definitely depends also on how many training points you have.
right, on the sample size. Yeah, so that's just another aspect to think about.
Okay, so I don't think I'll be able to cover all of decision trees today, but I'll get started. And then we can continue this in the lecture. Okay, decision trees are another method that we can use to.
So on that picking K based on the sample size, you only pick K based on the sample size of the training set, right? You're only building the model on the training, right?
And I'll let you respond to that.
Yeah, so you pick a K that works well on the training, and then you see, does that K work well on the test data set? But when you do it on the test data set, it's an entirely new data set. So all I was trying to say is like the pictures that Alex was showing about, tracing out the boundary between the two. I was just saying that, if you want to get like the same decision boundary, if your sample size changes drastically, then you just, would change K according to the sample to get that same decision boundary.
Oh, okay.
It's a minor point. But just something to be aware of if you're actually going to implement the cross-validation like in your projects.
Okay. Great. So now let's talk a little bit about decision trees. And I'm going to briefly introduce a new data set. This is kind of also a very common data set in machine learning, the Titanic data set. So we have the Titanic, obviously everybody's aware, sunk, and a lot of people, like the majority of passengers and staff actually died in that accident. And so the question is, can we maybe make prediction of who survived and who died based on the attribute of those people? So we would assume, given that this is kind of like, there are certain factors, like maybe the first class is higher up on the Titanic, so they did maybe like had an easier way of getting out, that this wouldn't be completely random, right? Or we would assume that social convention would emphasize that children should be saved and women should be saved, especially in the
Okay, I think we lost Alex, but I think he'll be right back. Let's see. Okay, yeah, sorry about that, everybody. I'm not sure what happened there. Let's give him a few more minutes. Maybe he's having difficulties connecting. In the meantime, anyone have any questions or comments on K&N classifiers?
Are you going to show us how to run a test set on a model? We've learned a few ways to build a model, but then how do you apply the test set to that model?
Oh, I don't think I fully understand the question.
You can split data set to test and train, and then you can build a model based on train. But how do you take that test data set and apply it to that model? We've learned OLS for making a model, but how do you apply tests to that model?
I think Alex just showed code for that for the K&N, right? Where he was looking at, doing the train test split. Let me double check that. Oh, Alex is back.
Yes.
Okay.
Looks like my internet gave up. Okay, I think with 5 minutes left, it doesn't make a ton of sense to start a new method. What I'll do instead is we'll just do questions if anybody has questions about projects or about K&N or cross-validations, and we'll teach about decision trees in an upcoming classification lecture.
So next week, do we have a lecture on Thursday?
No, we don't. Like next week is kind of like our spring break light. We found it pretty hard last time, and lots of students told us that it was really hard in the fall to not have a break at all. And so we're not doing classes next week, and there's also like this 2-week span for the homework to kind of take a little bit of a breather for everybody.
So that's just Thursday, right? So we do have a lecture this Tuesday.
No, we have no lectures next week.
Oh, okay. No. Okay.
Yeah. I see a question about office hours. Some of the office hours will be available. I think I unfortunately won't be able to do office hours next week. Just look at the calendar. All of the office hours that are scheduled in the calendar will be held.
I'm having some issues installing Graphiz, the thing we were told to. I was just curious if I get some help at just any point.
Yeah, maybe you can post any errors you get and also tell us about your operating system on Slack.
Okay.
For me, it installed easily on Mac, so I'm not sure I'll be able to help you.
I'm on Mac as well.
Okay, do you have Homebrew installed?
I tried installing Homebrew, and then I tried to do brew install Graphiz, but I got an error. I'll put it in the Slack right now.
Okay, that's weird. And like Graphiz is, we only use Graphiz in the decision tree piece for visualizing the trees. So you can still use decision trees without Graphiz. So if you can't get it to work, it's not a big deal. And you can look at the figures that I provide. But of course, if you want to use like decision trees in your project, you might want to be able to look at the trees. But yeah, if you have any error messages, post them on Slack, please, and we can try to help out. Okay, looks like there aren't any questions. So thanks everyone, and I'll have a good break.
There's one more question in the chat regarding audience. I feel like I'd be interested in hearing that answer from you.
I have a hard time understanding you.
Sorry, she's saying there was a question in the chat. That was my question about what level we should communicate the final project on.
Okay. So you should kind of like, you can definitely assume that like you're talking to the TAs and the staff and to your fellow classmates, right? So you should, like, if you discuss your project, you can discuss like things for like how do you do your model selection and so on. That is totally fine. You should probably like still make it clear what you learned in like a generally accessible way, but you can definitely be technical in the rest of it.
I see. So if our tool maybe was intended to be public facing, we could still communicate our methods and everything in a technical way in our video.
Yeah, so I think there's two things, right? There's like if you have a public facing website or something like that, that is independent of like your, well, not independent, but you will still have a Jupyter notebook where you describe your process, right? So your public facing piece can be kind of like as generic or as general for a general audience friendly as you like, but you should still tell us what was your, like, why did you make certain decisions and so on in a technical way. And that can be separate from anything that is public facing.
Great, thank you.
Should each cell on the Jupyter notebook that we deliver have some sort of interpretation or narrative?
I again had a little bit hard of a time understanding you with your microphone, but like there was like, you should definitely talk about the narrative. Is that what I?
Yeah, the interpretation that you're asking for. I was wondering if we need to give that interpretation after each cell or section.
We can't say that you have to do this after each cell or section, but it could be that you have it in multiple places, right? You could say, hey, I'm trying out this particular method for classification, and then it didn't work out, right? That's fine to keep in your project. And then at that point, you should say, okay, here's what we tried out. We found that it doesn't work, and now we're moving on to something else. If you want to do some interpretation about your data set, like that might fit at the end, but it might also fit at somewhere in between. So let's suppose you're like looking at one aspect first. So like, is there a correlation between socio-demographic status and COVID rates? But then you might move on and look at something COVID rates over time, right? So you might have write about your interpretation at the right point.
Okay, thanks.